Hell yeah. So what we have here is 29 questions. What we're going to be doing is kind of learning about a different topic. We're going to be learning about chemistry. We're going to do a crossover. This isn't my main topic of study, but just using Google, we can ask questions and get to pretty decent answers. So let's just read this first one. Are any chemical reactions neither endothermic or exothermic? And so what I'm getting at here is I want to know, and it says no. In every chemical reaction will pick up energy or release energy. So that's kind of fascinating. I want to talk about chemistry in terms of like Newtonian mechanics, because you could have an elastic collision between two particles of mass. A pool ball could run into another pool ball and transfer all its velocity to that other pool ball. But when in a chemical reaction, you can't have the energy transfer from one atom to another atom without releasing energy or picking up energy. All right, next question. All right, so what do we have here? Why can't a chemical reaction be purely elastic? So that was kind of my question, and I don't know the answer to that. Yeah, that's a pretty decent question. All right, so moving on. Can a chemical reaction cause an electron to become excited? I was just wondering, because chemical reactions, if you do have this idea of atoms coming together in a chemical reaction, whether it takes energy in to produce some output, or if you combine or separate atoms and protons and neutrons and electrons and stuff like that, then you're going to get maybe energy released. But like that, what I'm interested in is, like, I kind of understand from a kinetic energy, one type of energy is just the temperature increases, and the temperature increase is a Newtonian phenomenon where you just have molecules vibrating or moving. You basically have mass with velocity. That's kinetic energy. And but when an electron becomes excited, let's dive in more, because I think I go down a line of questioning. Does an excited electron change a material's temperature? I was kind of curious about that, and it said yes. And then so I wanted to know. But basically this idea of temperature, what's going to happen is, like, one individual particle can't have a temperature. It has to be a collaboration of particles. So can a group of particles have excited electrons and have no change in temperature? And this says yes, but with a caveat. It talks about the overall kinetic energy. So this doesn't really answer my question, is like, basically, I think the answer to this one is no. If you have excited electrons, you're going to get, in my view of Newtonian mechanics, you're going to get mass that's now moving. And then so this next question should answer it. Is an excited electron a change in kinetic energy? And yes, when an electron goes from like one orbital to a higher orbital, because it has more energy, it's going to become excited. And that is an increase in kinetic energy. Next question, is temperature the internal kinetic energy? This says no, temperature is not exactly the internal kinetic energy. It's just kind of the average internal. So maybe let's go on to the next question. What type of internal kinetic energies are there? This was just going to give me not the very greatest answer, but translational and rotational. Not the answer I was looking for. How about this one? Does an atom with an excited electron vibrate more? You know what I mean? And, because I just wanted to know from a Newtonian perspective, does it actually move more? And yes, because the electron is in a higher energy state, dynamic environment, more vibration, sweet. Okay, so let's see what we got for questions. Is absorbing photons considered a chemical process? Now I'm just fascinated with what is chemistry? You know what I mean? Like, that's basically what I want to know, is like, what's the limitations of chemistry, or what's the classifications of chemistry where chemistry doesn't become chemistry no more? But yeah, so if you absorb a photon, it's still considered a chemical process. And why? Let's see, it's photochemical. Because it's probably because you're, I guess chemistry is the makeup of particles, of atoms, or also particles, because you've got protons, neutrons, and electrons, and the energy associated with those groups of particles, atoms, molecules. Okay, is chemistry the study of physics where the net number of protons, neutrons, and electrons remain the same? And this says no, is not the physics where, because in chemical reactions, the number of protons in atoms usually stays constant, but the number of electrons can change, creating ions. But this really didn't answer my question. I was more interested if, because I literally sometimes don't know like what the fundamentals of the universe are, so we'll get to that in another question. Yeah, this is it. Will there always be the same number of neutrons, protons, and electrons in the universe? Since the Big Bang, are the number of those three always the same? And our current understanding is yes, they will always be constant. But we're going to ask some further questions. And I'm gonna kind of. I think I asked pretty good questions, so stay with me. We're going to talk about mass and how mass can change. So the mass of the universe isn't constant. In a very peculiar way. But anyway, let's get on with it. It is impossible to create matter from energy. So our current understanding is, it's not accurate. Einstein related E equals mc squared, that if you have a pile of energy, it's equivalent to mass, And if you have mass, it's equivalent to pure energy. But more questions. Nothing in our current universe is shown to create mass from energy, like stars and stuff. So no, that is like there is no known process in the observable universe that can actually take energy and make a new proton, make a new neutron, make a new electron. So it's kind of fascinating. Cool. So two let's see what we got here. So two hydrogen atoms. To separate two hydrogen atoms is a chemical process. Back to the definitions of what is chemistry. So chemistry is you got some particles, protons, neutrons, and electrons, and we're going to, change them up. Obviously they have energy because of their composition, like where the electron is orbiting. It could be in higher orbitals, in higher states. But if I have to separate two hydrogen atoms are very stable. They want to be together, but to separate them it is a chemical process. Cool. Does it take a lot of energy to break hydrogen bonds? And I was surprised about this is no, it doesn't. It actually takes a lot of energy to separate. Well, no, I can't say things that I don't know, but is because these bonds are considered weak bonds, and they're what type of bonds are they? Compared to covalent bonds, I don't know what type they are. Anyway. To chemically combine two hydrogen atoms requires energy. And so I'm glad this statement was not true. So no, if I combined two hydrogen atoms, due to this chemical process, these two hydrogen atoms, as H2 now, will be in a lower energy state. So the two individual hydrogen atoms were higher energy, and that's the whole idea of chemistry. So this kind of cool, this line of thinking really gives me a very fundamental understanding of what chemistry is. I have a proton and an electron here. That's a hydrogen atom, and I have a proton and an electron here, and they have an energy related to them. Even though the electron's in the lowest orbital, cool. They're in their lowest state of energy. But when I combine them, they actually mesh together so well. And so we're going to ask some questions about why. Why does H2 have a lower energy than just two separate atoms of hydrogen? And it says because, what does it say? Because their electrons are shared, but more specifically, the electrons, it talks about how, oh, maybe I should just read this, but it feels like this isn't the one. I think I asked the question again. The attractive forces between the electrons and nuclei in H2 molecules are greater. Oh, so the attractive forces between the electrons and the nuclei. And this is interesting because the nuclei is a proton. Well, yeah. Oh, never mind. Sometimes I get confused because an atom can be made up of two protons right next to each other, which is kind of crazy because protons are two equally charged like particles, and they don't want to be anywhere near each other. And so that kind of brings in the gluon, you know what I mean? I'm glad they called it at least the gluon. It's like glues them together. It's kind of fascinating. But yeah, so an electron and a proton, for sure, they have a bond force between them, but in this H2 molecule, that bond is going to be greater, and that attractive force is going to be greater. All right, hell yeah. All right, next question. Because it takes energy to break chemical bonds, is that a form of potential energy? And it says, yes, because it takes energy to break chemical bonds, the energy stored within the bonds is considered a form of potential energy. So now we have these two hydrogen atoms. I mean, we have H2, two hydrogen atoms in this, combined. And it's going to take energy to break those bonds. But the fact that they're bond together, they have this potential energy. And I don't like that. I don't know. This is where I can't give you... I don't know. So we go down this line of questioning. If I had energy to break a chemical bond, do I get energy out? Because it seems like if you got potential energy between those bonds, it's like, hey, is that energy that could be released? It seemed to me like it was like Einsteinian mass energy, like rest mass energy. Just the fact that they're bound together, that if you're able to break that bond, you get like all this energy out. And actually, it's quite the opposite. When you add energy into both of those hydrogen atoms to actually break them apart, and now they're just on their own. Then I get kind of confused of like, well, is potential energy of a chemical bond considered an energy sink? You know what I mean? It didn't seem like it's usable energy. If I have to actually, pour more energy in to actually break that bond. And the opposite is true. If I got two hydrogen atoms and then they combined, the energy is actually external. Like the two hydrogen atoms combined will have lower energy, but they have to release, a little poof of energy somewhere in the universe. You know what I mean? So this idea of bonds having potential energy, I'm not quite up to speed on that. So how can chemical bonds have potential energy if it takes that amount of energy to break that bond? I think we just need to read this. So chemical bonds have potential energy because the energy is stored within the arrangement of atoms when they are bonded together, meaning that when a bond is broken, energy is released as the atoms separate and move to higher energy states. So I think on a different day, I'll have to go down a different line of questioning because this isn't true for the hydrogen atoms. So maybe there is some molecules that when you break them apart, they actually go into a lower energy state. Would that make sense? Because if I have these two hydrogen atoms and I combine them, I get energy out. And let's go full circle. I'm not going to go back to that first question, but okay, all chemical reactions are either endothermic or exothermic. So they fit into those two categories. I just chose one where I have two hydrogen atoms and they have more energy, and when I combine them, hey, maybe that's a special case. I mean, there's a lot of chemical reactions that are probably like that, but now I get energy out. Like when those two come together, they go into a lower energy state, and then I get energy popping out. But I'm sure you could have the opposite. I'm sure if I had two atoms, I would actually have to heat them both up, and then maybe they combined in that way. So I had to add energy into them. Now I have this combined molecule, let's say, and then when that molecule breaks its bond, the energy will now be released. So I think that'll be kind of my take-home aha. All right, so an individual proton, neutron, and electron always has way more energy than when they are combined. And that was just back from this one. It seems like the hydrogen that wasn't combined, but I don't know if that's going to be 100% true, because we just talked about how maybe you can combine two different atoms and they're going to be in a higher energy state because you added energy in. But this question was pretty decent. So if I just have the individual neutron, electron, and proton, they will have, yes, they will be in a higher energy state. When they combine, they have slightly less energy. Cool, almost done. So is the rest mass energy of an atom always in the lowest energy state? So yes, this idea of Einsteinian rest mass energy is always in its lowest energy state. Let's see what we got. So are two separate hydrogen atoms in their ground state? Are two separate? Yeah, so if I have two separate hydrogen atoms, they have more energy than when they combine, but are those two separate hydrogen atoms, are they in their ground state? Yes, the electron is moving about that, that lowest orbital. Cool. If two hydrogen atoms are in their ground state, why, when they combined, are there lower energies? And yeah, this was the better one. It says because the electrons from each of the atoms are able to partially occupy the space between the nuclei, creating a stronger attractive force between the electrons in both nuclei. I think that's kind of interesting. I would almost want to see a picture of this. But that which outweighs the repulsive force between the positively charged nuclei. Yeah, because if you have two, because if you, like we just said, you have a proton and an electron, but now you just have two protons that just join together in an H2, molecule of hydrogen. Those protons don't want to be anywhere near each other, but because we have the electrons and because of that idea of partially occupying the space. All right, hell yeah. 3 more questions. And this was a pretty good way to end it. Is the bond between proton and electron the energy of rest mass? This is kind of interesting, because I wanted to know what the hell rest mass was. And is it... Because I confused myself just the other day. It's just like, well, is rest mass the energy that is required to bond protons and electrons? And no, the bond between a proton and electron is not directly to the energy of rest mass. The equals mc squared is due to the fact that the proton has mass, the electron has mass, the neutron has mass, but that's it. Just the fact that it has mass is equivalent to this amount of energy, equals mc squared. All right, so 2 more, and then these are pretty good ones, though, because this is good. Because do a separate proton and electron have a different mass than when they combined? I was kind of curious about that. And it says, yes, when a proton and electron are combined to form a hydrogen atom, the combined mass is slightly less than the sum of their individual masses when separated, due to the concept of mass defect. Now, this might not be... I'm just going to say, there could be a huge caveat here that this is maybe the way I'm asking it, even a nonsensical thing to ask, because there's when talking about particles, you want like a rest mass equivalent, you know what I mean, where you say like, hey, that's the rest mass of the object of the particle that you're talking about. This was interesting. I would have to research more about this, but then, this is my last question then. So then the mass of the universe is not constant because of this idea of mass defect. And it says this statement partially correct, but while mass defect does occur at an atomic level, where a small amount of mass is converted to energy when the nucleon binds together, it is generally considered that the total mass of the universe remains constant on a cosmic scale due to the principle of mass-energy equivalence. So, yes, you can't create nor destroy mass, but I was just kind of interested in the idea of the fact that, what does this say? That when they do combine, their masses are more or less. I think we need to go back to that. Yes, when a proton and electron are combined to form a hydrogen, the combined mass is slightly less. Okay, so a free proton and an electron has more mass. Interesting. So, and when they combine, the mass is slightly less than the sum of their individual masses when they separate. But I think the take-home point that I kind of learned was that our general understanding is that, cool, you might have a slight fluctuation in the quantity of mass, whether they're separated or combined, but the individual, like if you're counting up protons, electrons, and neutrons, that number does not change. So there's no appreciable change in mass in the universe. And for sure, the energy of the universe is considered to be constant due to that mass-energy equivalence. And that's just kind of what we know about. But yeah, that's fascinating because, I mean, like chemistry and physics down at the atomic scale, I'll just talk for a couple more minutes, but just so you don't get confused, is just like, okay, so I do have these individual building blocks, but I could have a proton and an electron, electron orbiting that proton. But if it's in an excited state, I could actually add more energy into that. That electron can occupy different higher energy states. And I can say that the energy of that proton and electron is more. And so that idea of, like, where does energy go? How do you store energy into things, and how is energy released? And if it is released, it has to be released into other forms of energy. So, all right, hell yeah. And I don't know, this is the tip of the iceberg, because I probably lose my mind when it comes to, like, all I can, like, fathom. I like chemistry because you still actually talk about mass. You know what I mean? You have a chunk of mass, and then you attribute an energy to it. From a Newtonian perspective, if that mass is jiggling and vibrating, hell yeah, we can understand that, hey, that's mass and velocity. You know what I mean? So if, because there's a lot of chemical reactions where the temperature will change. Either it'll get colder or it'll get hotter, depending. And if it gets colder, the molecules slow down. They're vibrating less. Hotter, they vibrate more. And so from kinetic energy, it's very easy to see. And so it's just kind of interesting, like, where the different forms of energy go. Vibration, electrons can be excited, and then just to see, like, well, that's kind of the same thing. More vibration is just, it's just kind of fascinating. I'm fascinated in the Newtonian perspective, because, like, the whole topic of chemistry, I think, can be, too difficult to swallow for people if they just don't have, like, a fundamental basis. So we did it. We did 29 questions, and basically I'm just doing this to get a more fundamental understanding of what the subject is. And from this line of questioning, like, I might stumble across just quality questions that people in the field of chemistry probably don't ask them for themselves, because you can get super tunnel vision just in very nitty-gritty technical details where, just to have an overarching, especially when it comes to, like, hey, I've been into Newtonian mechanics. How does Newtonian mechanics, bleed over into this idea? Because chemistry for sure talks about energy in a form of kinetic energy, and I think we did it. I did a long video on thermodynamics, but for sure, if something increases in temperature, you get more Newtonian classical motion, and more mass moving, more mass with velocity is a higher kinetic energy. All right, hell yeah. So, all right, we're done with this one. But yeah, leave a like if you want me to do more of these. 29 questions is probably too many to do, but, maybe 20 questions, do the 20 questions. All right, you should do this for yourself. It's not bad. Some of these AIs are going to be wrong, so you got to be worried there. Also, any of my videos, hell yeah, we're just learning to learn. If my stuff is wrong, I'll actually watch my videos and get to a right answer faster. So if you see stuff that's absolutely just garbage wrong, let me know, because I think that's the best way to learn, especially if you got some embarrassment where you're just like, whoa, I can't believe I posted that. I'm not going to change my post, but definitely just working to get better. All right, so hell yeah, thanks for joining me, and guess what? That's a video.